Good CPU performance in audio processing needs your help, your interaction and your understanding. Hi. Audio processing is one of the most difficult tasks to handle for a computer. It's very sensible about timing. Nothing is more noticeable in a bad way as underruns and resulting crackles and gaps in the playback. A computer handled this task by filling a buffer. The size of the buffer is set in the Audio tab, depending on the used drivers of your sound card. The smaller the buffer, the harder the CPU has to work to fill this always in time. The bigger the buffer, higher latency, but give the CPU more time to do its work. There are no general rules how to set the buffer length. It depends on your situation, on your needs. But one can say as low as needed, but as high as possible. I guess the most users are in the same boat like me, just trying to reduce the latency between hitting a key on the MIDI keyboard and hearing the produced sound. People with complex in and out routings, for example out of the box into hardware units and back into the box, have different demands as these buffer sizes add up. But setting the buffer smaller as really necessary just stresses your CPU without enhance anything. While we're at it, we have to touch a little bit on the topic about sample rates. Working with, for example, 96 kHz instead of 44.1 reduces a latency of 512 samples from 12 to 5 milliseconds. Shorter time to fill the buffer means the CPU has to work harder. Before you blindly fall into this trap, the higher the better. Take a step back and regard this topic again. A good start to search would be the term oversampling. Going deeper into this topic would go beyond the scope of this video. But I cannot urge you enough to first inform yourself what's really behind before going the high sample rate route. My advice would be, keep the sample rate at 44.1 kHz for music and 48 kHz for movies, until you really run into a problem which cannot be solved otherwise. The CPU meter in FL Studio shows you how much time is already taken from the CPU to fill one buffer. A buffer size of 512 samples equals at 44.1 kHz nearly 12 milliseconds. This 12 milliseconds equal 100% in the CPU meter. If the CPU meter shows a usage of 50%, this means that the CPU needs already 6 milliseconds to fill the buffer by doing all the calculations. You've got only 6 milliseconds left. In nowadays multi-core CPUs, the complete workload is spread to the different cores. But if one of them fails to do all the calculations in time, the whole buffer cannot be played in time. You get buffer underruns. A buffer cannot be played until it's completely filled, and if just a single core isn't ready in time, the playback has to be delayed until it's ready. Stuttering, crackling, gaps in the playback are the consequences. Because of that, the CPU meter always shows you how much processing time the hardest working core has already taken. Forget about the CPU meter of your operation system. The only meter which counts is the internal one. The workload for FL Studio depends on what goes on in the whole program, divided into two main threads, the GUI and the audio processing. What counts most for us is the audio part. Here we can help the CPU having to do as little calculations as possible, but we can as well destroy a lot by making wrong decisions. There are first generous settings which influence the CPU load. As already mentioned, the smaller the set buffer size and the higher the sample rate, the less time the cores of your CPU got to do their work. Set it to a value which takes both sides into account, making work comfortable for you, but trying to not stress the CPU more as needed. If a certain latency feels good enough for you, there's not a single reason to set it even lower. Even if there is a need in certain situations to go lower, that doesn't mean you have to stay all the time at the lower value. If a sample rate of 44.1 or 48 kHz provides you the needed quality, there is no reason to set it higher. Live resampling quality. This affects only the sampler channel when playing in different pitches. This influences only what you hear when you play back the project. For normal playback, this option shouldn't be set too high. 16 or the default 24-point sync should be enough. The render options have their own settings, which you can set as high as you like. Just note, there could be a slight difference in sound between the live playback and the final render if these options are set differently. Higher settings doesn't always mean it sounds better. It depends what you like best. Multithreading for generators and mixing should always be turned on, as well as Smart Disable. Try on your system if performance improves if you enable mix-in buffer switch, triple buffer, and safe overloads. I have mine always turned on. Force high performance power plan should always be turned on as well, and the power plan should be optimized for your system too. Second, there are considerations on a project base. PPQ settings. I made 2 detailed videos on this topic. Links are in the description. Consolidate stuff as much as you can. Audio playback hardly take any CPU cycles. Besides of CPU improvements, rendered audio does have many advantages or many editing types impossible to do with MIDI or live processing. Render and replace patterns can be an option too. Related to consolidation, make use of special features of FL Studio. One of the greatest improvements, but hardly used or even recognized, was the implementation of its own sample robot. Create direct wave instrument. Sampled instruments mostly don't take any CPU and can take you from a CPU load of 25% to 1%. Smart Disable as much as you can. Many third-party plugins and sometimes FL natives consume a lot of CPU even with doing nothing. And not everything is playing in your project all the time. You can use a macro switch Smart Disable for all plugins as often as you want. It just turns on Smart Disabling but never off. If you run into trouble with certain plugins which create a longer tail like delays and reverb, you can exclude them in the plugin options or for VST plugins permanently in the wrapper options. If you are experiencing CPU load not getting better with Smart Disable turned on, please follow these rules. You have to mute patterns or tracks feeding these plugins in the playlist or turn off the generator in the channel rack. Otherwise, MIDI data or audio gets sent to the plugin, which will then stay active. Muting the channel in the mixer doesn't help, as it happens afterwards and not before the plugin receives the data. Mute automation sent to this plugin, and delete initial control settings. As long as it receives any of this data, the plugin cannot be disabled. Do always Smart Disable following these rules after consolidating. Choose the right plugins for processing and set them properly. Plugins can be CPU friendly, but sometimes CPU hogs. Especially third-party analog modeling plugins can be quite CPU intense at times. Decide if you really need the most specialized plugins eating your CPU for breakfast, if you just want to process a background sound, which is barely hearable in the project. Or if you got more or less the same sound from 2 different plugins, but one takes much more CPU, why not take the other one? Edit synth presets to your needs. Often presets are created to sound good in isolation. In a complete project though, high unison settings and long release tails are sometimes more of a hindrance than a help, as they make everything too dense. You can save a lot of CPU by reducing unison and release to what you really need. Less can be more at times. Don't use real-time stretch mode if not necessary. Pre-rendered modes do not use any CPU, while the stretch mode works and is processed in real time. More information in my 2 videos, 5 guidelines for time stretching. As usual, links in the description. And now it gets really interesting. How to make your project multi-thread compatible. This might sound simple at first glance, but turns out as a quite tricky beast. First, we have to look into simple physics of audio processing. This is best visible in Patcher. In audio production, we are working with signal chains. What is a signal chain? A source provides a sound. This could be a generator or a simple input port in Patcher, which is routed in this case to the output. This is the simplest form of a signal chain in digital audio processing. But this chain can of course be expanded. We can insert an EQ and afterwards a compressor. Now we got 3 components, but all in a single line. The sound goes from left to right. This dictates a certain logic. The generator creates a sound, which in this example gets first processed by an EQ, then by a compressor. This is the most important part in signal processing. The latter process cannot start until the previous hasn't finished. The EQ cannot work before the generator created the sound. And the compressor shall process the already EQ'd signal. Because of that, it has to wait for the EQ to finish. This is a serial sequence. None of these processes can happen at the exact same moment. Nothing happens in parallel, but after each other. Because of this logic, it makes most sense if every complete signal chain, everything which has to happen in a row, is processed in one thread. Which means everything happening in a single signal chain is processed on one and the same single core. The more complex the chain, the longer this core has to work, the higher the CPU load. Keeping a signal chain as simple and as short as possible helps to reduce the overall CPU load. Always remember, as soon as one core fails to deliver in time, the whole system breaks. Decide yourself if there's really a need to put 25 plugins in a chain to process a sound. If so, and this could of course be the case, perhaps it's a good idea to build up this chain in a way that you can easily consolidate this part. Let's look at multithreading. This means distributing the workload onto multiple cores. Distributing the work onto multiple cores make only sense if you can process something in parallel, in the same moment. In a single signal chain, one cannot start to work before the other has finished. There's nothing happening in the same moment. If I would force the program anyway to spread the processing onto multiple cores, it would have to act like this. The generator is calculated on core number 1. The EQ by core 2 and the compressor on core 3. The single components are splitted onto multiple cores. The generator on core 1 creates the signal. This is step 1. So far so good, everything is fine. The EQ is now processed on core 2. During step 1, while the generator is busy to produce its sound, the EQ is blocking core 2 by sitting around and doing nothing. It's just on hold. It sits around and cannot do anything because it simply needs first the sound coming from the generator. Not before the generator provides a signal, the EQ can start to work. This is step 2. Because of the same reasons, the compressor is blocking core 3. During step 1 and during step 2 by doing nothing. It has to wait all the time for the generator and the EQ to finish their work. Only then it can start to work itself. So what happens here if we put it onto the same timeline? The core for the generator, work and finish. The core can be used for other tasks. The core for the EQ, wait, and then work and finish. The core for the compressor, wait for the generator, wait for the EQ, and then work and finish. What did I gain here? Nothing. I could have used just core 3 for doing everything. It would have taken the same amount of time. But here I blocked with waiting cycles multiple cores which could have been used for other stuff. This cannot work. That doesn't make any sense. One signal chain, one thread, all on the same core. Nothing else can improve this. But if I add a second signal chain, a second generator goes into a second EQ, and then into a reverb. This second signal chain can be processed in parallel. While generator 1 creates its signal, generator 2 can create its signal in the same moment. While EQ1 processes a signal in its chain, EQ2 can do the same on the second chain in the same moment. While the compressor works in chain 1, the reverb can do its job on chain 2 in the same moment. This makes sense. No time wasted, no cores wasted, multi-threading at its best. Now we go one step further. What happens if we route the second chain differently? We interrupt it before the EQ and send it into chain number 1. The two generators are still working in parallel, means on two different cores. But then the signal of chain 2 gets part of the first chain, and its further processing will be restricted to the core of chain 1. Now we route it again differently. We leave the chains as they were before, but instead routing chain 2 directly out like we do with chain 1, we route it now into the EQ of chain 1. What happens now? There are still two cores involved. Let's look now first at chain 2. The generator creates its signal, which gets processed by EQ2, and then the reverb. After that, the process stops. On chain 1, it's now different. In the same moment when generator 2 creates its signal, the same happens with generator 1. Perfect in parallel. But then it happens. First, we have said, the EQ of chain 1 has to wait for the generator to finish its work. Now it has to wait even longer. After the core has calculated the signal created by generator 1, the core has to wait. It has to wait for the second EQ and has to wait for the reverb to finish. Only when chain 2 has finished its complete processing, means after the reverb is calculated, the EQ on chain 1 can start its work. After the EQ, the compressor can now work without any further delay. This situation is worse. By CPU performance, we speak about processing time available. The longer the calculations last, the higher is the CPU load. In a perfect parallel routing, all calculations on all cores take the same amount of time. Let's assume for a second that all components, generators, EQs, compressor and reverb would take the same amount of time, of for example 1 millisecond. This previous example would be perfect multi-threading for two cores. 1 millisecond plus 1 gives us 3 milliseconds on chain 1. And 1 millisecond plus 1, 3 milliseconds on chain 2. In our last example, we got the same 3 milliseconds for chain 2. But on chain 1, we got now 1 millisecond for its own generator. Plus wait for EQ2, 1 millisecond. Plus wait for the reverb, 1 millisecond. Plus 1 millisecond for EQ1. Plus 1 millisecond for the compressor. 5 milliseconds on chain 1. Chain, and therefore core 1, need now nearly the double time to finish the whole processing. More complex routings are always negative when it comes to CPU performance, as calculations taking longer, and cores get blocked by wasted waiting cycles. Of course, in reality, this all happens millions if not billions times faster and will be hardly noticeable. But it's important to understand these weaknesses. Let's look into the mixer. At the very end, a mixer track itself is a single signal chain. The sound enters at the top, goes through the plugins, through the EQ, and final stage with panning, volume, phase, width and delay. This whole chain will be always processed by one thread, and because of that, by one single core. But what happens if we do inter-track routing with sense, buses and sidechains? Let's take an example of 4 tracks, processing with different plugins and settings. Every single signal chain will be processed on its own core. I add now a patcher preset I've made to make the CPU load visible. On track 1, the CPU load raises to 27%. Now I do the same on track 2. The CPU meter stays nearly the same. Why? It's a separate chain, a separate thread, processed by a second core, multithreading. On to track 3, CPU the same. On to track 4, CPU the same. I have just 4 cores. Now all of my cores are already occupied. If I now put one onto track 5, the CPU nearly doubles. After all cores were already used by tracks 1 to 4, the operation system had to reuse one of these cores, and the new patcher instance came on top of another, and on top of the CPU load already present. Now I can play this game again. Adding new instances onto track 6 to 8 do not have any impact at all. But at track 9, it adds again on top of that. Think always in multiples of your cores. I have 4 cores. Loading a patcher instance onto one track raises the CPU load as much as putting an instance on 4 tracks, as they are processed in parallel. Having an instance on 5 tracks raises the CPU as much as having an instance on 8 tracks. On 9 tracks, it's the same like on 12 tracks, and so on. To make things easier, we are now back to one instance on just tracks 1 to 4. 26-27% CPU. Now we sum the latter 3 all together on a bus channel, track 1 in this case. I have 4 cores. I have the same amount of tracks. I didn't insert any other patcher, but the CPU now nearly doubled. All processing which happens on the single tracks themselves stay in parallel and on separate cores like before. But every processing which happens on the bus itself adds on top of that. From the moment we routed the signals together, we took out track 1 out of the multithreading. It's now in serial after the processing of the 3 other tracks. First, the 3 other tracks have to process their own chain. And after this work is done, the processing of the bus channel can start. So what FL Studio now did is taking the thread of the bus and put it into the thread of the mixer track, which will be finished last. Why into this thread? Because the whole bus processing cannot start until the latest signal has reached it. Remember this patcher example? Remember that this EQ has to wait until the complete second chain finishes? This is the same situation. Every time you create a send or create a bus, you break the compatibility of multithreading to some degree. The more buses, the more sends you use, the worse gets the multithreading performance of the whole project. Remember again, as soon as one core of the CPU struggles to finish its work in the needed time, you start to get underruns. As soon as you route tracks to other tracks, you put the workload of the receiving channel out of multithreading and put it onto the same core which processes the sending tracks which finishes last. And the deeper your track routing gets, the worse it gets. Please don't get this wrong. It's not my intention to tell you shouldn't use buses or sends. And the example here is way overdriven. In a real project, buses and sends will hardly raise your CPU load by 25%, but more by 1 or 2%. Of course, inter-track routing, sidechains, buses and sends are hardly avoidable in many situations. This is the reason why getting right all the other mentioned settings and measures is so important, especially consolidating and smart disable. Only these measures can give you enough headroom to deal with the restrictions which inter-track routing causes. Everything must be regarded at the very end as an entire package. Getting all this right can help a lot. Making wrong decisions or being forced to ignore one or the other part make the whole performance worse, bit by bit. Thank you for watching.